Projectile motion. This is what really gets level 2. So this is the first little video we're going to do. Let's pretend this is a water rocket, one of my super duper water rockets, and we launch it at an angle, as we do sometimes. Now, you've already studied vectors and velocity, so you're thinking to yourself, I know you're thinking this, we can break that down into two components. And the components, we could break it down to 2 or 3 or 5, but we could break it down. But we choose the horizontal and the vertical components. So that's sort of like the original vector is like the red one. It's a combination of a vertical velocity and a horizontal velocity. Now, if gravity acts straight down, gravity acts that way, then the gravity can only affect the vertical component. It can't have an effect on the horizontal speed. So gravity is a force and it acts on an object, but it only acts in the direction of the gravity. So the force, which is equal to mass times acceleration, in this case mass times g, because the acceleration near the surface of the earth is g, which is 9.8 meters per second, acts vertically down towards the center of the earth. This can only affect the vertical component of the velocity. So when we do these calculations, we split it up. So although we know that this object does this parabola, at each point, if we look at the velocity, the horizontal velocity will stay the same because it has never been affected by the gravity. So the horizontal velocity, this one, will stay the same the whole way. Now the vertical velocity, which started off this big, once we get up to here, it's still there, but it's much smaller, then much smaller, and at the very top, it's 0. And then it actually starts to be vertically down. So although the force never changed, and thus the acceleration never changed, the acceleration was always vertically down. What did change was the vertical velocity. First, that acceleration slowed it down, so it was positive up, getting smaller, smaller until it stopped. Then it started to get negative, bigger, bigger as it came down. So the vertical velocity changed. It went from positive up to negative down, and it went from big to nothing, and then got bigger again. The horizontal velocity stayed the same the whole way. So when we do these projectile problems, what we do is we split up the components into horizontal. So if the velocity is v, we could call the horizontal vh, and we could call vertical vv. So we have to split it up to do a lot of the calculations you're going to be asked to do. And what determines how long a projectile is in the air is totally the vertical velocity. And so let's put some numbers to this, and let's just start. We'll probably do a couple of videos to cover everything. So if the velocity is 25 meters per second, and the angle is 50 degrees, theta equals 50 degrees. Let's calculate the components. So the components, VV, so we've got that, 50 degrees, and we've got V equals 25. So VH equals 25 times cos of 50 degrees, and VV equals 25 times the sine of 50 degrees. So let's do that on our calculator. Let's just do that quickly, or slowly. 25 times cos of 50 equals 16.06. I'll call that 16.1 meters per second. And the vertical velocity, 25 times sine of 50 equals 19.15. I'll call that 19.2 meters per second. So we've now worked out the components for the vertical velocity and the horizontal. Sorry, that's vertical. Vertical velocity, horizontal. So we can put this one as being 19.2 and 16.1. So the vertical velocity is going to be acted on by the acceleration. And the acceleration is equal to 9.8. Vertical velocity is 19.2. Now the question is, have we done anything wrong there? And we have. Because gravity's down, but the vertical velocity is up. So we've got to give them a direction. So I'm going to make my velocity up positive. So that means my acceleration is negative. So now we're going to ask ourselves, how far does it go up? And we have to now remember our kinematics equations. So let's always go to this one first and see if it helps. And it does. Well spotted. We start with VI, or in this case, VV. See, we've sort of split our equations into two different parts. Because the vertical component has an acceleration acting on it, we have to use our kinematics equations for it. So I know when something goes up, and I want to know how high it goes, right? Then I know at the top, if I call that VF, then I know it's equal to 0. And I know it started with a velocity of 19.2 meters per second. So I can do my equation now. I can say VF squared, 0 squared, is equal to VI squared, 19.2 squared, plus 2 times acceleration, 9.8, times distance. But remember, the acceleration was negative. So this whole section here is going to become negative, because 2 times negative 9.8 times d is going to be negative. So I can actually do that calculation like this. I can say, oh, okay, 19.2 squared, 0 equals minus 2 times 9.8, which is 19.6, 19.6d, right? So I can go add 19.6d to both sides, and I've got 19.6d equals 19.2 squared. So if I divide both sides by 19.6, I can find out how high it goes. So first thing I do is 19.2 times 19.2, that's 19.2 squared, divided by 19.6, and I've got 18.8. So I now know it goes 18.8 meters high. All I had to do was use that one equation. Now the next thing they might ask you is, how long does it take? Now, what information have we got? We've got the fact that it went 18.8 meters, right? And we know that gravity equals minus 9.8. We know it started off with a velocity of 19.2 meters. So let's see if we can find an equation. And you look through the equations. I'm going to look at this one. Df equals Vi plus At. Alright, now sorry, Vf equals Vi plus At. If we look at this equation here, we again know that Vf equals 0. We know that Vi equals 19.2 plus A times t, which is 9.8 times 2. But again, that's negative. So again, we can go 9.8t, because I bring that negative onto the other side, equals 19.2. So now we've got a t that is equal to 19.2 divided by 9.8. Got a t of 1.95, so I'll make that 1.9 seconds. 1.96 seconds. That was to go up. It took 1.96 seconds. Now, so what have we worked out? We worked out that it went 18.8 meters up and that it took 1.96 seconds. So that means 1.96 seconds to get up, 1.96 seconds to get down, because it is a symmetrical thing. So if we've got 1.96, then the total flight time to get down is 3.92 seconds. So the last part of the problem that they can ask you is, how far did this actually go? So when you're looking at a projectile, all right, we worked out that it went 18.8 meters up, that this whole flight time was 3.92 seconds. Let me just bring that up. Its whole flight time was 3.92 seconds, right? So we need to go right back to our first sheet of paper where we worked out its horizontal speed. And we said its horizontal speed was 16.1 meters per second. So it had a velocity like that, which was made up of the initial horizontal speed, which was 19.2 that way, and 16.1 that way. So it has a speed horizontally which isn't affected by the acceleration. So we can just use our real simple formula. V equals d over t, or d equals vt. Now v is 16.1 and t is 3.92. So we can go d equals 16.1 times 3.92. And we get a range of 63.1 meters. So from an initial problem, we've worked out a few things. We've worked out the height. We just got an initial velocity. We worked out the time to the top of the flight. We then doubled that time to get the range. The equations we used, initially we used this one. That gave us the height. We used this one to give us the time. And once we had the time, we used this one. Sorry, I keep getting too low, don't I? I use this one to give us the height, this one to give us the time, and this one to give us the range. And those are pretty common aspects from any projectile problem.